So let's take a look at an example. We want to use the Gram-Schmidt algorithm to convert a known basis of some vector space V to an orthogonal basis for the same vector space V. So this is exactly what the Gram-Schmidt algorithm does. It takes a basis that we know, which isn't necessarily orthogonal, and it turns it into an orthogonal basis. It transforms it into an orthogonal basis that spans the same space. All right? So we're just going to apply the Gram-Schmidt algorithm step by step. So step one, let me label the vectors in my original basis V. My original basis B. Call them V1, V2, V3. Okay? So I'm going to find vectors F1, F2, and F3 that are orthogonal and form a basis for the same space V. Now, according to the Gram-Schmidt algorithm, to find F1, all we do is we're going to set it equal to one of the vectors in my original basis. In this case, V1. Okay, technically it could be any of these, but we usually go in order. So I'll start with V1. Okay. Not very interesting. Doesn't get interesting until we start working with F2. To get F2, we want F2 to be orthogonal to F1, but we want F1 and F2 to span the same space that V1 and V2 span. Okay, so what I'm going to do is I'm going to take V2, and to make sure it's orthogonal to F1, I'm going to subtract the projection of V2 onto the space spanned by the orthogonal vector we already found, F1. Okay, so I'm going to take the component of V2, the orthogonal projection of V2 onto vector F1. Okay, and since that's the only orthogonal vector I've already found, that's the only one I have to subtract. Okay, so let's do the computation of that. So V2 is 0, I'm sorry, 1, 1, 1, 1. V2 is 1, 1, 1, 1 minus V2.F1 over norm of F1 squared times F1. Let me just state here what F1 is for the record, 0, 0, 1, 2. Okay, so the dot product of V2 and F1, so here's V2, here's F1, and if we take the dot product, you can see pretty quickly the dot product is going to be 3. So minus 3 over the norm of F1 squared. So 0 squared plus 0 squared plus 1 squared plus 2 squared is 5. So norm of F1 is square root of 5. Squared is just 5. Gets rid of that square root. So I get 3/5 times vector F1. 0, 0, 1, 2. Okay. Do a little vector arithmetic. I'm going to get 1, 1, and then 1 minus 3/5. That's 5/5 minus 3/5. I get 2/5. And then 1, and then negative minus 3/5 times 2. So that's 5/5 minus 6/5. That's going to be negative 1/5. Okay, so that's F2. Now I have two vectors, F1 and F2, that are orthogonal to each other and span the same space as the original vectors V1 and V2. I'm not done yet though, right? Because I've got a third vector. So we need to do the same thing for V3. Now, before I do that, I do want to point out the main point of the Gram-Schmidt algorithm is to get a basis that is orthogonal. Now, if we scale a vector, it doesn't change direction, it just changes its magnitude, right? If we multiply a vector by a scalar, which means if I multiply this vector by a scalar, it will still be orthogonal to F1 and it will still span the same space. So what I could do is instead of taking F2 to be 1, 1, 2/5, negative 1/5, just to make the numbers a little bit nicer, let's take F2 to be 5 times 1, 1, 2/5, negative 1/5. And so I'm going to get 5, 5, 2, negative 1. Now you do not have to do this step, okay? But if I take F1 to be this vector and F2 to be this vector, those two vectors are still orthogonal. They still span the same space. I've just made this one 5 times as long as the algorithm initially would give, just to make the computation a little easier. Okay? And that's going to be nice when we get to the third step, because I'm going to need to use vector F2 in the computation. All right? So for F3, what we do is we take V3, and then we want to take out the part of V3 that is part of the span of the vectors that have come before, that we've already found. So what I want to do is I want to subtract the projection of V3 onto F1. And subtract the projection of V3 onto F2. Okay, so vector V3, let's plug in. Vector V3 was 1, 0, 1, 2. 1, 0, 1, 2. And then I'm going to subtract the dot product of V3 and F1. So F1 is 0, 0, 1, 2. V3 is 1, 0, 1, 2. If we take the dot product, we are going to get 1 plus 4, that's 5. So we're going to get 5 in the numerator, divided by the norm of F1 squared. So here's F1. The norm of F1 is 0 plus 0 plus 1 plus 4, adding the squares of the components. So that's 5. Square root of 5 squared is 5. So norm of F1 squared is 5. Times vector F1, which was 0, 0, 1, 2. Okay, that's nice. Now I need to do the same thing here. Okay, so that's V3.F2 divided by the norm of F2 squared times F2. Okay, so V3, I need the dot product of V3 and F2. Now, again, it doesn't matter whether you use this one or this one, but which one would you like to use if you're taking a dot product? Probably this one, right? Fewer fractions. So let's take the dot product of V3 with F2. So I get 1 times 5 is 5, plus 0 times 5 is 0, plus, if I can scroll this so I can get both in there, plus 1 times 2 is 2, plus 2 times negative 1 is negative 2. So I'm just going to get 5, right? Divided by the norm of F2 squared. Again, I want this one. It doesn't matter which one of these you use again, as long as you're consistent. If I'm going to use this F2 to take the dot product, I need to use that same F2 throughout, okay? And we really don't want to take the norm of that one. So again, very nice that we could do this. Okay, so the norm of F2, I have 5 squared is 25, plus another 25 is 50, plus 4 is 54, plus 1 is 55. So I'm going to square root of 55 squared, I get 55. Times F2, which is 552 negative 1. So let's do the vector arithmetic, get our final answer for F3 here. I'm going to start by just simplifying. Negative 5 over 5, that's just 1, right? So I'm just subtracting these two vectors as is. So 1 minus 0 is 1, 0 minus 0 is 0, 1 minus 1 is 0, and 2 minus 2 is 0. Okay, so that's these two. I still need to subtract this. Now 5 over 55, that reduces to 1 over 11. We have 5, 5, 2, negative 1. So if I subtract these, I get a common denominator here. 11 over 11 minus 5 over 11 is 6 over 11. And the rest of the subtraction is easy. 0 minus 5 over 11 is negative 5 over 11. 0 minus 2 over 11 is negative 2 over 11. And 0 minus negative 1 over 11 is positive 1 over 11. And this is fine for F3, but just as before, any scalar multiple of this vector would still be orthogonal to the two previous vectors. It would still, with the two previous vectors, still span the subspace. So rather than using this vector, I'm going to multiply this vector by 11. That way I could get rid of any fractions and make it look a little prettier. Okay. So instead, I'm going to set F3 equal to 11 times this vector that I found, which is 6 over 11, negative 5 over 11, negative 2 over 11, 1 over 11. I'm just going to make it a little bit longer than it was before. It's still pointing in the same direction, so it's still orthogonal to the other vectors. Okay. All right, so I have an I have F1, I'm taking this as F2, and then I'm taking this as F3, and they are all orthogonal to each other. They all form a basis by the Gram-Schmidt algorithm, and therefore my orthogonal basis, my B prime is my orthogonal basis, is going to be these three vectors. So 0, 0, 1, 2. That's F1. And then the F2 that I chose was this one here, which is 5, 5, 2, negative 1. And F3, I took 6, negative 5, negative 2, 1. That's my final answer. Okay, that is an orthogonal basis for the subspace. Now, it's orthogonal because each of these vectors are orthogonal to each other. F1 and F2 are orthogonal. If you take their dot product, you'll get 0. F1 and F3 are orthogonal. If you take their dot product, you'll get 0. F2 and F3 are orthogonal. If you take their dot product, you'll get 0. We did see in the last section that an even better basis would be an orthonormal basis. Remember, an orthonormal basis is also an orthogonal basis, but it has all the vectors as unit vectors. So once you get an orthogonal basis, if you want, you can take it and get an orthonormal basis. We've seen that we could take these vectors, and any non-zero scalar multiple of these vectors would still give us an orthogonal basis. So if I normalize these vectors, I would get an orthonormal basis. So this is an orthogonal basis. And that's what the problem wanted, is an orthogonal basis. So that's all I need to do. But if I want an orthonormal basis, I could normalize each of the vectors.